right, so Unit 2. Unit 2 is probably our most important unit. That said, okay, there weren't a lot of, like, a whole bunch of separate concepts. Everything kind of went into kind of 2 or 3 categories. Okay, the first half of the unit was dealing with Newton. Okay, Newton's first law, which is basically just inertia, an object at rest remains at rest as long as there's no net force acting on it. Okay, Newton's second law, which tells us that net force is the vector sum of all forces and relates to acceleration as a factor of mass. Okay, and then after that, we went into work energy theorem and conservation of energy. Right, those are basically the things that are in this unit. We talked about power for one day, and there was one question on your unit exam about what power was. Okay, and that's the extent of the unit, right? Being able to do those things. Okay, so there's not really a need for me to go into a whole bunch of detail about here are all of Newton's laws, and let me read the notes over one more time. Okay, because we don't really, that's not what's really being tested. Okay, what's being tested is your ability to apply these concepts, okay, to basically problem solve. Right, so what I'm going to do instead is put some problems on the board, and then we'll use those as examples, and then we can kind of work through them as examples of here's a Newton's second law kind of problem, here's what we need to remember about Newton's second law, or Newton's first law, or work and energy, and stuff like that instead. Okay, so to start it off, I'd like you to try that one. I think we did one like this at the end of class yesterday, but it's like a vector addition type of problem, but it's to do with Newton's second law. Okay, the one we did was like the 2 sleds pulling, and it was almost due west when we were done. Okay, so for a Newton's second law problem, typically our givens come in the form of a free body diagram. All right, so we've got a 60 kilogram box. It's being pulled due east by 200 newtons worth of force. And it's being pulled at 50 degrees north of east with 300 newtons worth of force. Okay, so that would kind of be my givens. Is that diagram going to help me to get my net force? No, I'm still going to have to draw a vector diagram in order to get my net force. Okay, so I'm going to start out with the 200 newtons due east, and then I'll put tail to head on that, the other force, 300 newtons. I think that's roughly the scale. That might be slightly more than 50 degrees, but okay, so this will be y, this will be x. Okay, and then we'll have our net force is the result, the vector sum of those 2 forces. And I'm just going to draw the box up here so that it's out of the way. Okay, so we would have a vector diagram like that coming next. Then we got to find our x and y components. Green x is 200 newtons east, and y is 0 newtons. Okay, and then for our blue one, right, we've got x is going to be the cos of 50 degrees because it's the adjacent side times 300, and y will be the sine of 50 degrees because it's the opposite side times 300. Okay, 192.84 newtons, and that is east. Right, and then we'll have our sine of 50 times 300. Okay, it should be 229.81 newtons, and that will be north. Okay, and now we can find out what our Rx and Ry are. Our Ry is going to be really easy, okay, because there's only one part of the trip where it goes north. Okay, so Ry is going to be the same as blue y, 229.81 newtons. Rx is going to be the vector sum of 200 and 192.84, so 392.84. now that I've got my resultants x and y, I can find f net by doing a Pythagorean theorem calculation. So 229 squared plus 392 squared. Okay, obviously I'm going to keep all the decimals in my calculator when I do that calculation.
You did 192 instead of
392. Yep. Well, luckily that's easy to fix. 392. Take that, calculator. Okay, 455, and we have two significant digits. Actually, sorry, we're not even there yet. We're looking for acceleration. So 455 newtons. Okay, and then I've got to find theta. Okay, theta for me will be the inverse tan of the opposite side. This time I'll actually use 392.84. Okay, divided by 229.81. Okay, that'll give me my angle. So Alright, so we're looking at 60 degrees. For me, that's east of north. Okay, and then we have to find the acceleration. That's the Newton's second law part of this. Okay, where we just have to go F net divided by m equals a. So our 455 divided by 60. So we've got an acceleration of 7.6 meters per second squared at 60 degrees east of north or 30 degrees north of east. Okay. Everybody all right with that one? Okay. These were a static question. Okay, that we went over. What do we have to remember about a static situation?
F net is 0.
F net is 0 because acceleration is 0. Okay, so the vector sum of all the forces involved in this situation is 0. Find the tension in these cables if this angle here is 100 degrees. Okay, so as we said before, the key to this one is realizing that the net force is 0. The second key to this one is realizing that the upward force that neutralizes this force, gravity, okay, has to be split equally between the two cables. All right? So while this upward force in total is 981 newtons, okay, it's actually 490.5 newtons per cable. And then the angle gets reduced to 50 degrees for each cable. Right? Now that we know an angle and we know a side, we can figure out what the tension in the cable is, because it'll be equal for both cables, okay, simply by doing a little bit of trigonometry. Okay, we know the adjacent side and we're looking for the hypotenuse, so we know that the cos of 50 degrees equals 490.5 over the tension in the cable. All right, so all we have to do is go 490.5 newtons divided by the cos of 50, and that'll get us the tension in the cable. Okay, so 490.5 divided by the cos of 50. And it tells us that the tension in each cable is 7.6 times 10 to the 2 newtons. Remember that tension is how tight the cable is, and it didn't ask us which direction is the cable pulling on the sign, in which case we would need to add a vector of 50 degrees from vertical or something like that. But in this case, it just asked for tension. The cable is pulling that hard.
Wouldn't the sig dig still be 3 though? Because we were given 100.
Sorry, you were given 100 degrees. I went with 50. Sorry, you're right. Yeah, it would be 3. So it would be 763 degrees. All right. Any other questions on that one? Okay. Try this question. I'm not even going to spoil it for what kind it is. And see if you guys can identify what type, because that's an important skill on a final exam. And if you have a look at a question and go, oh, that's a Newton question, or that's a work energy question, or that's a conservation of energy question, or maybe it's one of the three. It probably is one of the three. You have to figure out which one.
Is the,
Actually, it's not a conservation of energy question. Sorry, I should have explained a little more. It's a work energy theorem question. Okay? There's a force. Force applied. Okay? Something is pushing it up the ramp. Okay? That applied force is 500 newtons up the ramp. Okay? The energy of that box is changing from the bottom, where it's going 3 meters per second, to the top, where it is 10 meters higher. Okay? And we don't know what speed it's moving at. Could be faster, could be slower. It'll depend on how much work that 500 Newton force can do over the 20-meter length of the ramp, or distance of the ramp. So it's a work energy theorem problem where this 100-kilogram box is being forced up the ramp.
can you also use as an incline plane, where you take
You
the-
can, but it's a lot more work, believe it or not. Finding all the forces and doing all of that, and then doing the net force, yeah, it's a lot more work to do it that way, but you can. It's totally legitimate to do it that way, okay? I'm gonna solve it as a work energy theorem problem, because it's simpler. Okay. All right, so work is being done, which means the energy between the bottom of the ramp and the top of the ramp is changing, because work's a change in mechanical energy. So we have to set up our work energy theorem in that work is a change in energy. Okay, and so what that's going to look like is force times distance, because I have the force 500, I have the distance 20 meters, okay, is going to equal my final mechanical energy minus my initial mechanical energy. Okay, everyone all right with that so far? Okay, so I'm going to expand this out so that it looks like this. Right, I'm going to have EP final plus EK final minus, okay, EP final, or sorry, EP initial plus EK initial. Now, this is what?
Not relevant.
Not relevant, because it's zero. You're at the bottom of the ramp. You don't have any initial potential energy. All right. So now I know that what I'm looking for, which is the final speed, is part of kinetic energy final. So I need to get this isolated, okay, before I expand out one more time. So I'm going to add EK initial over here. So I'm going to have work plus my initial mechanical energy equals my final mechanical energy. Right? Does that still make sense, right? The change in energy plus my initial energy should equal my final. Okay. I'm looking for something that's part of EKF, so I'm going to subtract the potential energy final back over here. So now I'm going to have force times distance plus EK initial minus EP final equals EK final. And now I can expand it out for the last time,
Why don't you take the angle into consideration?
because I don't need it to do it this way. If I do it as a Newton's second law question, which is longer, okay, I will need it. But I'm not going to do it that way, because I don't need it. All right, so now I'm going to have this expanded out. I'm going to have force times distance plus 1/2 mv initial squared minus m times g times h final equals 1/2 mv final squared, and then I just have to divide both sides by half of m and take the square root. Okay, that'll get me VF. All right, so work energy theorem is like basically one step. I'm only doing work energy theorem. I'm isolating VF. Okay, so if I plug in my numbers, 500 newtons times 20 meters plus 1/2 times 100 times 3 squared minus 100 times 9.81 times 10 divided by 1/2 times 100. Okay, that'll give me VF. So when I plug all that in, okay, I'm going to have 1,000 minus 0.5 times 100 times 3 squared. I put in 100. 1,000. And I put in minus when I should have put in plus. Plus.
That's also
God, come on. Plus 0.5 times 100 times 9. A shortcut. Okay, so there's my initial energy plus my work. So that's my essentially final. Okay, and then I'm going to subtract from that 100 times 9.81 times 10. Okay, and then I'm going to yes. Oh, it's 10,000. 500 times 20, not 2. Frustrating myself here. Okay, let's start that over again. I'm certainly not making this seem like the shorter method because it keeps screwing it up. Okay, so 10,000. I have the right number of zeros because I started out with 100. Okay, plus, and I need 0.5 times 100 times 9. That's better. Okay, minus 100 times 9.81 times 10. Good, I don't get a negative number. Okay, divided by 0.5 times 100. Oh God, I can't believe I put that in. I didn't just write in 50. I'm ashamed. All right. It's not going much faster, is it? Okay, and that's okay. It gained a lot of what? Potential energy. It's 10 meters higher than it was before. Okay, basically we just exerted enough force to get it up the hill plus a little bit. Okay, so that's the way to solve it as a work energy theorem question. It's the way I would have meant for it to be solved. Okay, does it mean you can't solve it as a Newton's second law question? Absolutely not. You can totally solve it as a Newton's second law question, but it's a lot more work. Okay, because instead of just doing work as a change in energy, I need to put in a free body diagram. I need to put in gravity, which I'll have to calculate. I need to get my F parallel, which I'll have to calculate. Okay? Then I've got to put in my applied force and my F parallel. Okay? Which I'd have to, then I'd have to do a net force calculation. Okay? Then I'd have to get the acceleration after that. And then I would have to do an acceleration calculation where VI was 0. I'd be looking for VF. I would know the acceleration and the distance, and then I would solve for VF at the top. It's 5 steps at least, okay, instead of 1 energy step. Okay, now if you did it that way on a test, you would get exactly the same answer, and it would be perfectly valid to do it that way. Okay, it's meant as a Newton's second law question, or sorry, as a law of conservation of energy question. Okay? But it's perfectly valid. If there's more than one way to do it, both ways are perfectly valid. All right, everybody all right with that idea? Okay. Okay, you know I love inclined planes. There might be one on the final. Okay, so classic Newton's second law situation here. Okay, we know the acceleration, okay, is 1.7 meters per second squared down the ramp. Okay, so down the ramp. Since I know the mass, what can I calculate right now that will be useful later? F net, yeah. Okay, so let's get that right now because it's something that's always important. Okay, m times a, so 200 times 1.7 would be 340, okay? 340 newtons, also down ramp. All right, other forces that are involved. We are looking for the force of friction. What force is pulling down the ramp? F parallel, okay? Since the net force is down the ramp, F parallel has got to be the bigger of the two, okay? So I've got to calculate F parallel using that little triangle that is present on every inclined plane. The hypotenuse of that triangle is the force of gravity, okay? The internal angle is the same as the incline, and the opposite side is F parallel. This side's F normal, but I'm not going to need that, okay? So I've got to find force of gravity. 200 times 9.81 is going to be 1,962 newtons. Yes, I did that right. Okay. All right, so I've got that. I'm going to go sine of 30 times F parallel, sine of 30 times FG. That should give me that F parallel is 981 newtons, if my math is correct on that one. Okay, and then we are going to use that and the sum of all forces. Okay, so if I want to calculate the force of friction, I'm going to take F net and subtract F parallel, so I'll have 340 newtons down the ramp minus 981 newtons down the ramp, and that's going to give me a negative number, which is good because negative is up the ramp, okay, which is the direction of the force of friction. So 340 minus 981 is going to give me negative 641 newtons, or 640 newtons up the ramp, but I only have two significant digits because the 30 only has two, so 6.4 times 10 to the 2 newtons up the ramp.
How can the force of friction be more than the F net if it's moving down?
It has to be. F net is, like, F parallel is the force pulling down the ramp.
Right.
It's bigger than the force pulling up the ramp, which is why my F net is down the ramp, 340 newtons. It's okay for forces inside the problem to be bigger than F net. They usually are, right? Especially if they're acting opposite each other. Yeah, does that make more sense?
Yeah.
F parallel is bigger, and it should be. Okay, any other questions on that one? It's a pretty standard inclined plane type of question. Okay, pulleys. I would like the acceleration of the 2 kilogram mass. Okay, the other mass is 0.750, that's not 750. Okay, 0.750 kilograms, and assume the force of friction is 4 newtons acting on the 2 kilogram mass. Okay, so I want the acceleration of the 2 kilogram mass. For this one, we got the force of friction as one of the forces. We got the force of gravity here as the second force. Okay, so we're going to have 0.75 times 9.81 to get that one. Okay, so 7.35 or 7.36 newtons. Okay, once I have that, okay, really what's going on here is this. 2.75 kilograms worth of mass is being pulled one direction by 7.36 newtons and resisted in the other direction by 4 newtons worth of force. That's really what's going on when you have a pulley. Okay? It's a system, both masses accelerate together at the same rate. Not necessarily the same direction, obviously that's not the case here, okay? But at the same magnitude of acceleration. So I'm going to calculate my net force. Okay, my net force is going to be 3.36 newtons, okay, in the direction of the 0.75 kilogram mass. And then I'm going to find the acceleration by going net force divided by the total mass of the system, 2.75, 2.75 kilograms. Okay, so when we do that, okay, we're going to have our 3.3575 divided by 2.75. Okay, so we get an acceleration of 1.22. No, sorry, we only have one significant digit. 1 meter per second squared, right. Why can I give a direction on this one? because I asked specifically for the acceleration of the 2 kilogram mass. Okay, had I asked for the acceleration of the system, then it would have to be 1 meter per second squared, and that'd be it. Okay, if I asked for the 0.75, it'd be down. Right? Since I specified which mass I wanted the acceleration of, I would have to put a direction on it. Okay, everyone all right with that one? Okay, it's a sled. Imagine it's a sled going down a frictionless hill. Right? So it starts at the top. We don't know how high the top is, okay? But it's moving at 4 meters per second at the top. When it is 10 meters from the bottom, it is moving at 16 meters per second. Calculate the height of the hill. What kind of question is it? Conservation of energy question. Okay, how do I know it's not a work energy theorem question? There's no work being done, there's no force present, there's no distance given. Okay, all of those things would be necessary for a work energy theorem question. Okay, so it's a law of conservation of energy question. EI equals EF. Okay, so that means EP initial plus EK initial equals EP final plus EK final. All of those have a non-zero value, okay, so they're all present. What I'm looking for is part of EP final, so I'm going to subtract EK final over to start things off. Whoops, I did that wrong. I want to subtract EK initial over to that side, sorry. EP initial equals EP final plus EK final minus EK initial, okay? And so we're going to have m times g times h initial equals m times g times h final plus 1/2 mv final squared minus 1/2 mv initial squared. M is in every term, so we can get rid of it, okay? Even though we were told what the mass was. And then I just divide both sides by g, okay? And that'll leave me with hi. So hi will equal 9.81 times 10. Plus 1/2 times 16 squared minus 1/2 times 4 squared divided by 9.81. Okay, so our initial height of the hill is 22 meters. Okay, everyone all right with that? I think we've covered pretty much all the types of questions now that you could run into, okay, from this unit. So I'll take questions from you guys if you got something else.
Was Newton's third law the next unit?
No, sorry, Newton's third law was also in this unit. Sorry, I forgot to cover that. Newton's third law, yeah. So every action is an equal and opposite reaction. That's Newton's third law. On your unit exam, you had a 2-box question, okay, where you had to figure out what the force back on the first box was or something like that. I'm not asking that on the final. Okay, that doesn't mean you don't need to know what Newton's third law is for like a simple thing. Like in the multiple choice on that exam, you had the question about the mosquito hitting the windshield. That's a Newton's third law kind of thing that you could see on the final. Okay, something simple like that, where the force on the bug and the force on the car are equal. Okay. I'm not going to get into specifics on the type. Like there's this question. I'm going to say there's a Newton's second law question for sure. Okay, whether it's an elevator or a pulley or an inclined plane or you know, one of the vector addition ones like we did at the beginning, could be any one of those. Maybe it's more than one. Yeah. Okay. Right, what else, guys? Okay, couple of reminders, okay, in case this applies to you. Okay, remember that Thursday at 3:30 is the last day to hand any overdue assignments in for grading. Okay, I've been getting kind of a flurry of them this week, which is good and bad that there were enough for a flurry, but good that they're coming in. Just remember that that's the last day to get stuff graded. Okay, help times during exam week. okay, are up on the board. So on Monday from 9 to 11, Tuesday from 1 to 3, and Friday, June 24th, 9 to, that's supposed to be 11, somebody erased part of that. I'm not going from 9 to 1 on that day. 9 to 11 on that Friday. Okay, those will be the times when I will be available for questions if you have them. Of course, if you come in, you have to stay all 2 hours. You can't leave. Of course not. Okay, you can come in and ask a question and leave. You can stay all 2 hours. It's totally up to you. But I will be here and my room is available at those times.
They have the opportunity during those times to look over old meeting tests.
100%. Yep. I will fish yours out of the pot if you want to come in again. Any other questions there, guys? Okay, I hope you have more questions than that on Thursday, because on Thursday it's all about your questions. Okay. So tomorrow, we'll do the circular motion and gravitation review. There is a chance that I will not be here, but I have a recording made and set up if I am not. Okay? And if I am not, Mr. Zanoni will be in here, and he will rule you with an iron fist, as he always does. You can't even say that with a straight face because he's such a nice guy. Yeah, so that'll be, if I'm not able to be here, that'll be the plan. But I got a sick kid at home, so I may not be here. Any other questions from you guys? Okay. Remember that you guys are writing your final exam in here, okay, on the morning of June 27th. So show up outside of my room about 8:45, okay, 10 to 8 at the latest. And be ready to go. Calculator and writing utensils is all you really need, okay? Because I will give you a fresh formula sheet for the exam. Thank you, Tony. Grab your phone. Okay. Right,
Can we just do one more work energy question?
another work energy theorem question. Okay. See if I can make one up on the fly here. That's weird. Okay, this will be 15 meters. I don't know. I hope this works out because I'm just pulling numbers out of the hat here. Okay? This is probably a really easy one, but work energy theorem problem. So we got a 50 kilogram mass sliding down a 60 meter long, 15 meter high ramp. Force of friction resisting that sliding with a force of 8 newtons. Calculate the speed at the bottom. Okay? This one I think could easily be solved both ways in about the same amount of time, just because I made it really simple. Okay. All right, so solving this as a work energy theorem problem, the reason I don't need F parallel is because I'm using gravitational potential energy change to take its place. F parallel acts over the 60 meters. Fg acts over 15 meters. So I can use it instead. It's changing the potential energy. Okay? If I want to do this as a Newton's second law problem, absolutely I need F parallel for that. It's part of the net force. But in this case, I don't need that because I'm not solving it from a force perspective. I'm solving it from a gravitational potential energy and kinetic energy perspective instead. I'm looking at it as there's energy that's different top and bottom, as opposed to there's how much force, it's going to accelerate it this much, and I'll calculate V from an acceleration perspective. That's why I don't need F parallel. Okay? Follow me there? Okay. F parallel, remember, F parallel is actually, that F looks weird. It's got an extra thing in it. F parallel is actually the, I keep drawing it wrong. Okay, so F parallel is the vector sum of Fn and Fg. Okay? By using change in gravitational potential energy, I'm effectively eliminating the need for that. Okay? It's the net force going down the ramp. Okay? Or sorry, it's not the net force, it's one of the forces going down the ramp. But I don't need to worry about it because it's not doing any work. Right? You follow me there? F parallel is the reason why we build ramps. They make work easier, but they don't make less work.
But wouldn't F parallel be the thing causing the box to go down the ramp?
No, gravity's causing it to go down the ramp from an energy perspective. From a Newton's second law perspective, yes, F parallel is the thing making it go
So
down.
then how do you set up FD equals energy final minus energy initial with this?
If there was no friction, F parallel times 60 would equal 60 times 9.81 times 15. F parallel does the work of gravity over 60 meters, where falling off would be the force of gravity working the same over 15 meters.
So F is just,
This is the only force causing work to be done. It's the one that's causing the change in energy. If this is a frictionless ramp, there's no change in energy from top to bottom.
can you just say that one more time?
Okay, because this is a friction, or because there's friction on this ramp, energy at the top and energy at the bottom are different.
Yes.
This is the reason why they're different. This is the force that changes the energy. If this is a frictionless ramp, F parallel does the same work down a 60-meter ramp that gravity does down a 15-meter fall. Does that make more sense?
Yeah.
So that's why I can solve it either way, but this way I feel is shorter and more efficient. Okay, on a question like this, it's maybe not a lot shorter because it's a very simple question. Okay, so force times distance, or work, is going to equal the change in mechanical energy. So that's going to be energy final minus energy initial. Okay, initially I only have potential energy. Finally, I only have kinetic. So I can say that the force of friction, which is the force doing the work, multiplied by the distance, which would be the length of the ramp, equals 1/2 mvf squared minus mghi. The change in energy. Okay with that?
Yeah.
Okay. So now all I have to do is solve for Vf. So I'm going to add mghi. So I'm going to force of friction times distance plus mghi equals 1/2 mvf squared So it's a quick solution versus if I had to do this with Newton, I got to find the angle, then I got to find Fg, then I got to find F parallel, then I got to find F net, then I got to find acceleration, and then I got to do an acceleration calculation. If I do work energy theorem, I got to do work energy theorem, and that's it. Yeah. If you're more comfortable doing it the other way, do it. There are certain ways for me to set it up where I could make that more difficult. If I'm really wanting this to be a work energy theorem question, I could probably make it so that it would be nearly impossible to do it as a Newton question. That'd be kind of a jerk move, but yeah, does that make a little more sense now? Okay, so when I plug in my numbers here, I'm going to have my 8 newtons, which is actually negative because it's back up the ramp, okay, times 60 meters, okay, plus 50 times 9.81 times 15, divided by 1/2 times 50, all square rooted. Okay, so if I'm looking at that here, I'm going to have, because the work is negative, so negative 8 times 60 minus 50 times 9.81 times 15. Whoop. Oh, right. Up here, right? Plus 50 times 9.81 times 15. Okay, divided by 25. Okay. All right, so at the bottom of the ramp, it should be moving at 16, I think we only have one significant digit, so 2 times 10 to the 1 meters per second, okay, at the bottom of the ramp. Okay? Everybody all right with that one? Okay. So the real trick to that one is that the work is negative. And I need to make sure that I show that because it's losing that energy. All right, making sense? Okay. So like I said, tomorrow, circular motion and gravitation. And we'll go over, some sample questions like bank curves, unbanked curves, vertical circular motion, some satellite questions, some gravitation questions, some field strength questions, things like that, okay? That will be game for the final, right? And then on Thursday, I will go over the exam in a bit more detail and give you kind of a breakdown of how many questions on this, how many questions on that, okay? What I will not do this time is say, here's the test, okay? I'm not gonna do that this time, okay? There has to be some mystery involved. All right, any other questions from you guys? Okay, well, you got 5 more minutes left here, so let's have you working on something, looking at the review package, reading over your notes or something.